So let's talk about your reference tables here. We've got different constants like Avogadro's number, gas constants. Remember to look at what the pressure is in to tell which one to use. Standard pressure, 1 atmosphere, is the same as 101.3 kilopascals, which is the same thing as 760 milligrams of mercury, which is the same. Standard temperature is 0 degrees Celsius or 273 Kelvin. Volume of 1 mole of any gas at STP is 22.4 liters. We also have heat of fusion and vaporization for water, specific heat of ice, water, and steam. We also have specific heat, density, and melting point for various metals. On page 2, we have density, melting point, and boiling points of 4 different organic substances. We have the same thing for some inorganic substances, and we have a reminder that 1 milliliter is the same thing as 1 cubic centimeter, and 1,000 milliliters is 1 liter. Both of these could be used as conversion factors. We have a periodic table. It is a little small, but I believe you and your young eyes will be able to see everything because I can see it with my reading glasses. Then we have various formulas, and we are told what the variables are. We also have the formula for percent error. We have solubility rules. So for example, all acetates, ammonium, chlorates, nitrates, and group 1 salts are soluble in water. All carbonates, chromates, oxides, and phosphates except group 1 and ammonium are insoluble in water. Okay, so these could be helpful. And then we have different kinds of reactions, and we have examples. Okay. Activity series. So fluorine is more reactive than chlorine, more reactive than bromine, is more reactive than iodine. With this activity series, again, what you're saying is, like, if these things have a chance, they will replace the hydrogen from cold water. These things will replace hydrogen from steam, so forth and so on. So basically, it's a way of looking at how reactive they are. Then we have your polyatomic ions here. And lastly, we have Roman numerals and the prefix that goes along with them. And then we also have solubility of various compounds. So for example, at 40 degrees Celsius, NaNO3, a saturated solution would be 100 grams of NaNO3 per 100 grams of H2O. Okay? Anything below that point at 40 degrees Celsius would be unsaturated. Anything above that point at 40 degrees Celsius would be supersaturated. Every point on the line at the relevant temperature is a saturated solution. You'll notice some things like NaCl is almost a flat line, not completely. Its solubility does increase with temperature, but it is fairly flat compared to most of the others. You'll also notice that the solid lines are, well, solids, and they go up with temperature, even in NaCl. The dotted lines are gases, and you'll notice that all of them go down with temperature. So gases are more soluble at lower temperatures than high temperatures. All right, so let's see here. Remember that if you have something like HCl or NaOH, this is a strong acid, this is a strong base. When you put these in water, they're going to dissociate into hydrogen plus ions and chlorine ions. This will dissociate into sodium ions and hydroxide ions. Okay, and so what that means is that a solution of these is, first of all, an electrolyte because it has ions and will conduct electricity. Secondly, because this has an increased hydrogen concentration, this is an acid. This has an increased OH concentration, so it is a base. Okay, notice that both of these are ionic. If you have something like C6H12O6, right, this is a covalent compound. It does not dissociate. Therefore, its pH is going to be 7. the pH of water because it doesn't dissociate. It doesn't give off hydrogen. It's not an acid. It doesn't give up OH, so it's not a base. Okay. Let's see here. Remember, if you have, let's say, 0.01 molar solution of HCl. This is a strong acid. It's going to dissociate completely, which means once it dissociates, you will have 0.01 moles of hydrogen ions per liter, and you'll have 0.01 moles of chlorine ions per liter. Okay, and if we wanted to figure out what the pH was, all right, we know this is an acid, and all right, and we know the pH is going to be the negative log of the hydrogen concentration. All right, and if we take the negative log of 0.01, I believe, I could be wrong, we're going to get 2. All right, and so then we know that pH plus POH equals 14. So we substitute in. If this is 2, this must be 12 to equal 14. All right, so that's how you can go from the molarity to the pH. All right, something else you might see is you have a situation of, let's say the OH concentration is equal to 1.0 times 10 to the negative 4th. All right, and for given, and we need to find the H plus concentration. That is our question. So we know that the constant for water is H plus, the concentration of H plus times the concentration of OH is going to be equal to 1.0 times 10 to the negative 14th. All right, so then we can solve, and the concentration of H plus is equal to Kw divided by the concentration of OH. All right, so then we substitute in. We know that's 1.0 times 10 to the negative 14th, and we were given the 1.0 times 10 to the negative 4. Oh, man. All right, and then when you divide with exponents, you're going to subtract those, and so the hydrogen concentration is 1.0 times 10 to the negative 4th. So then the pH would be 10. Yeah. All right, so that's how you can go from the concentration of one substance in the water to the concentration of the other substance, and thus the pH. I wrote this wrong. This should be 10, negative 10, because I subtracted. All right. If you were given remember the pH scale goes from 0 to 14. 7 is neutral. Anything less than 7 is an acid. Anything more than 7 is a base. All right? And strong bases are going to have a high pH and they're going to dissociate completely. That's why they give off so much OH ions. And strong acids are going to have a really low pH and they are also going to dissociate completely and give off lots of hydrogen ions. Both cases, they're going to be ionic, not covalent. So like KCl or HCl or NaOH or H2SO4. These are acids, well, acid, no, that's a salt. That's not acid or a base. Acid, that's a base because it's going to give off that OH rather. So remember, if you have, let's see, your known solution, let's say 5.2 molarity of H2SO4, and you're going to dilute it from 2 liters to 3 liters. So we started off with this 5.2 moles per liter, and then we're going to dilute it from 2 liters to 3 liters. So we just added a liter of water, okay? And we need to find the molarity. So the new molarity is our request. All right, so we're going to use the trusty M1V1 equals M2V2. All right, we know our first molarity was 5.2. That's an M. We know the first volume was 2 liters. All right, and we know the new volume is 3 liters, but we don't know the M2. All right, so we divide both sides by 3 liters, and we have 5.2 molarity times 2 liters divided by 3 liters. Liters cancel out. So then we're going to have 10.4 divided by 3. 3 will go into that like 3.1 times. So let's see here. If I work that out the old-fashioned way, that's 3, that's 9, he's 14. So it'd be like 3.4, and that'd be 12. That leaves 2. 3 are gone, that's 6 times, and so it'll be 18. That leaves 2. All right, so it's going to be like 3.46. So let's call it 3.5. And so that is the new molarity. All right. This is on your reference tables. Don't forget to use those things. All right. Let's say we had 15 milliliters of 0.5 molar NaOH. Okay, and we're going to titrate, and we're going to use that to titrate 22.7 milliliters of HCl. All right, and we need to find the HCl concentration. And that is our quest. All right. Now, to do this, the first thing we're going to do is, well, first let's talk about titration. So what a titration is you're going to neutralize, you're going to use the acid to neutralize the base, so the pH becomes 7. And so what you do is you have a long tube, right? And it's got like a little nozzle on it that you can turn, and you're going to let out drop by drop of, this is going to be the NaOH, okay? And you're going to start at a known volume, and then it's going to go down, and you're going to measure that. And that difference, they tell us, is 15 milliliters. Now, why does it go down? Because you're going to drip it into a beaker. And that beaker holds 22.7 milliliters of HCl. And you're going to do one drip, and you're going to swirl. And this has an HCl and an indicator. And it swirls, and the color changes, and then it fades. And so you do another drip, and you swirl, and it color changes, and it goes back. And then you do another drip, and you keep doing drip by drip until you get it perfect and it doesn't change anymore. And at that point, you have completely neutralized this acid with that base. And we can use this volume to calculate what this concentration was. All right, so first thing we're going to do is we're going to say, here's the neutralization reaction. HCl plus NaOH. This is the acid. This is the base. Produce NaCl plus H2O. This is a salt. Now, this happens to be the salt we put on our French fries, but not all salts are edible, okay? Plus water. All right, all neutralization reactions occur between an acid and a base, and a neutralization reaction always produces a salt and water. It will not always be NaCl, but it will be a salt. All right, from this reaction, let's see, here we go. We got 1 H here and 2 here. So that gives me 2 Cl. So I need a 2 here, 2 Cl. Oh, nope. I'm being wasteful. All right, I got 1 H, 1 H. That's 2 H's. 1 Cl, 1 Cl, 1 Na, 1 Na. 1 O, 1 O. So this is balanced. All right, I was trying to balance it, and it's already balanced. All right, so we have a balanced equation. That means we get this ratio: 1 mole of HCl for every 1 mole of sodium hydroxide. So, the moles of acid equal the mole of the bases. Okay, so we can use the mole of the acid times the volume of the acid is equal to the mole of the base times the volume of the base. Okay, that looks familiar, doesn't it? All right, now we're going to rearrange this for the volume of the acid. no, I'm sorry, the molarity of the acid. So MA is equal, we're going to divide both sides by VA. So MBVB divided by VA. And now we just have to substitute in. Okay, so we know that, let's see here, the molarity of the base way back here at the beginning was 0.5 molar. All right, and then that's times the volume of the base, which was 15 milliliters. I'm going to convert that to liters because remember, molarity is moles per liter. So that would be, we've got 15, remove the decimal, 1, 2, 3, so that'd be 0.015 liters. All right, and then we're dividing that by the volume of the acid, which is 22.7 milliliters. So 1, 2, 3, so that would be 0.0227 liters. And honestly, actually, it might not matter because if this is milliliters and this is milliliters, they're still going to cancel out, and I'm going to be left with molar. Well, let's see what we get. So if we've got 0.5 times 0.015, oof, 0.015 times 0.5. So 5 times 5 is 25. That's 5, 6, 7, and that would be 0, and that would be 0. And then we would have 3 decimal places. So it'd be 0.075. And we're going to divide that. You know what? I need a calculator. Alright, so 0.5 times 0.015. So, oh, see, I was off. 0.0075 divided by 0.0227 equals, alright, so I'm going to say divide by 0.0227, and that gives me 0.33. All right, and then that is the molarity of the HCl. Oops, that should be a lowercase l. All right, and I got the correct answer having converted these, but I think at least in this situation it wouldn't have mattered even if I'd left these as milliliters. We can check real quick. So that would have been 0.5 times 15, enter, divided by 22.7. And I still got the same answer. So at least in this situation, it wouldn't have mattered. All right. See if we can do 1 or 2 more. Let's see here. Remember that if you see this kind of weird U shape, that means micro, which is 10 to the negative 6th or 1 millionth. So it takes 1 million micrometers to equal 1 meter, for example. All right, and M, like mg or ml, okay? M, let's not put equal there. M is equal to 1/1000th or 10 to the negative 3 or 1/1000th. So it takes 1,000 millimeters to equal 1 meter. All right, remember molarity, capital M, is equal to the moles of the solute divided by the liters of the solution. Okay, it is straightforward. If you know the moles and you know the liters, then you can figure that out. If you're given grams, like let's say they say you have 30 grams of NaCl. Well, then you have to figure out the molar mass. And so you would say 30 grams. Now, the mass of sodium, if we look at our reference table, sodium has a mass of, let's call that 23. Chlorine has a mass of, let's call that 35. So 20, let's say 23 plus 35 would be 58. All right, so we know that 58 grams of NaCl is equal to 1 mole of NaCl. Our grams cancel out, and then we're going to have 30 divided by 58 moles. And when we say 30 divided by 58, that's going to give us 0.51 moles of NaCl. All right, now that you have the moles, you can plug that in, divide by the number of liters, and that gives you the molarity. That should be fairly straightforward for you. What time is it? Ooh, it's almost time to go. All right, let's see if I can get one more in here. Let's say we dissolve as much as possible of a certain solid in a quantity of water at room temperature. We pour some of the solution into the evaporating dish. An evaporating dish is just a little curved dish. You put some liquid in it, the liquid part evaporates, and then you're left with the crusty crystals in the bottom, the solute. All right, because the solute doesn't evaporate. All right, and finds the combined mass of the dish and solution. After it evaporates the water, she finds the mass of the dish and solid. Her data is shown below. Okay, so to do this, let's say the dish had a mass of 23.2. The dish and solution has a mass of 34.3, and the dish and the solid, so this is the dish and the solution, this had a mass of 34.3 grams. All right, and then this is the dish and solid, this has a mass of 26.0 grams. Right, and we know density of water is equal to 1.0 grams per cubic centimeter. So we know that the grams of H2O is equal to the volume of H2O. All right, so if we have 5 grams of H2O, then we have 5 cubic centimeters of H2O because it's a 1-to-1 ratio. See, 1-to-1 ratio. All right. Allison could use which of the following to find the solubility of the solid substance in grams per 100 cubic centimeters. All right, so we're going to say the mass of the solute divided by the mass of the solvent times 100. All right. Now, and then you have to set that up. But the part I'm not telling you is we're not given the mass of the solute. So you have to use the data and you have to figure out, like here, this is the dish and the solid. So how can you eliminate the dish from this mathematically and figure out what just the mass of the solute is? But that's what you're looking for, okay? All right, I hope this helps.